So it's a pleasure for me to introduce you Pedro Serena. He did his PhD in the University of Autónoma of Madrid in the 90s. Then he moved to Zurich, to IBM, for his postdoc. Then he returned to Spain as a professor titular. In the university, in the Autónoma University of Madrid. Then he moved to CSIC, to the Instituto of Materials Science in Madrid. And well, he is also in charge of some administrative things in the Consejo. He's here today because this afternoon in the CAISA Forum we are going to give a talk, both of us, about nanotechnology. The future is here. Okay. So then he will explain some new things about the nanotechnology and other things that are already known. But then I will ask some questions, interesting questions, and he will answer all of them. So I think it's going to be a good time this afternoon if you come. So all of you are invited to come. It's at 7 in the CAISA Forum. And this is more technical. It's for people with some knowledge in science, deep knowledge. And he's going to talk about molecules and big data, I think, or something like that. Graphene, all of these things. So thank you for being here.
Okay. First of all, I would like to thank IFISC and Rosa to be here, and also for the welcome pack. T-shirts and this kind of things. No, this is rather unusual in Spain, okay, this kind of thing. And I like to it. Okay, I will try to I don't know how many hours we have. Okay, we'll try to explain in 45 minutes, I hope so, more or less. Part of the work we have been developing in a consolidated project entitled Force for Future. Okay, and inside this project there are several collaborations, and the results here correspond to the collaboration among three groups. One from the Universidad Autónoma de Madrid, led by Pedro, okay, from the IFIMAC. And two of them, or another two groups coming from the Material Science Institute, one experimental group and another in computation, another computational group. Okay, we can say computational group. Well, I will, in short, tell you that this project is intends to develop new strategies in atomic force microscopy. Okay, using the so-called multi-frequency approach, in which the same cantilever, you can excite the same cantilever using several modes, and each mode is a channel for retrieving information, in particular mechanical information. Okay, then this is with the same measurement, you get 3, 4, 5 different magnitudes if you are using 3 modes or channels. And in particular, after this consolidated, the Ricardo Garcia team, who is the leader of the experimental group, have been awarded by the European Research Council with an advanced grant with this project that is just a continuation, but okay, they want to make some ecography inside of the cells in order to reconstruct all the internal part of the cells using the vibrations. Okay, then they use the deep as an exciter, okay? They excite mechanical waves, and they use the deep just in order to sense the coming waves And it's exactly an ecography, macroscopic ecography, but at molecular level. Well, this is the context in which we move, a combination of experimentalists and theoreticians and people making. Well, I should remind, just in short, that there are too many biomolecules to be tested with AFM, and we have focused on proteins, but proteins is also a very broad field. Okay, remind that the protein is composed by 20 amino acids, all have the same shape in this area here, okay, and they differ each other from these groups here that provide different functionalities to the amino acids. And then you have polars, nonpolars, hydrophobic, hydrophilics, okay, aromatics, etc. Then you can ensemble these amino acids through peptidic chain bondings, like this one here, okay, and then you can make any combination you want. These metabolics, okay, the proteomics, sorry. Then you have all the possibilities, all the combinations. In fact, this is the primary structure of protein, just correspond to the symbol description of the amino acid you have inside your protein. The secondary correspond to appearing inside the chain, not long-range interactions, medium or short-range interactions, and these interactions provide you some coiling of the structure or the formation of beta lamina or turns. And this provides these helical structures, beta lamina, etc. Okay, this is the secondary structure. This should be important later. And finally, the tertiary structure appears when these groups, okay, here in the amino acids in the Untitled Chapter, using electrostatic interactions or hydrogen bonds or very strong disulfide bridges or hydrophobic interactions. Okay, then all this set of interactions provide you these nice and complex structures at the end of the path. Okay? Well, combinatory is enormous in the sense that you imagine an amino acid with 1,000 elements, okay, it's protein with 1,000 amino acids, okay, and you have 20 possibilities, then you imagine the number, okay. In real life, numbers are different, and at this moment there are of the order of 100,000 structures recorded in the protein data bank. Then you get inside this protein data bank and you get the coordinates of these proteins. Okay, the public access. And these are increases of the order of 1,000 per month. Okay? More or less.
Are these natural proteins or?
In general, natural, but not only human. Okay. A protein data bank formed by many different species, even variants in the human species. Okay.
Is there a rough idea of what is the fraction of the total proteins that is this 100,000? I mean, if this is 10% of the total, or does anybody?
In the case of the human, is larger than that. Okay, it's of the 30%, more or less 40. You have a lot of work to do. Right? Okay. All these are obtained using X-ray or nuclear magnetic resonance. Okay, it's a very costly work to do there. But okay, this is we have a synchrotron, for instance. Okay, synchrotron, in fact, is one of the major uses of the fuses in synchrotron radiation are proteins at this moment, drugs in general. Well, but it's a little bit more the problem. We don't worry too much about protein-protein interaction, okay? But we are just more focused on protein surface interactions. Why? Because from the point of view of basic knowledge, there are a lot of problems to understand the absorption kinetics, the origin of the energy adhesion and the interactions that are involved in this adhesion. It's very important to know that if the absorption process will cause denaturation, for instance, or if there is some damage in the protein in order just to to modify the biological functions of this protein. Then from the basic knowledge point of view, there are a lot of interest, but from these challenges, social challenges and applications, okay, we can correlate the study of proteins on surfaces with the development of new bioimplants, the functionalism of nanoparticles, tissue regeneration, and biosensors. Then these are the reasons why the study of surface and proteins are so important. But okay, we have a lot of different surfaces and a lot of different proteins. We need to focus a little bit more on the problem. And this is just the end of our object, to understand two proteins, okay? The immunoglobulin type G, the IgG, which is a large molecule, is the most abundant structure in the immunological system. Okay, it presents this Y shape with two centers, two activity centers. Is hydrophobic. Is neutral upon absorption at physiological conditions, and in general, it prefers flat absorption in general. This means that the protein with this shape will prefer to locate this on the surface in general. The other protein we are studying, due to we have the coordinates of atoms, okay, there are some controversy in the human cellular albumin, and not for the bovine cellular albumin. Then we study this molecule that is the most abundant cell protein, is medium size, is not Y-shaped, is globular, is plenty of alpha helix, and in this case, this Y shape is plenty of beta lamina. It's hydrophilic, and it's charged. This means that we have two examples of very different proteins in our system. And of course, we'll study graphene, because it's just a fashion. Okay? No, there is a reason. My institute is just on the work program materials in graphene flagship. Okay? Then we need to put some results on the table. But this is not true. The real reason, the actual reason is not that. Is that we are just studying this system using the standard tools from biophysics, from biochemistry. Okay, for instance, for biochemistry, it's very difficult to reproduce some tungsten oxide or silicon oxide surface, for instance. They are dealing with carbon. Then biophysical tools are well designed to reproduce carbon. Okay, graphene is carbon. This means that we can use the same tool that usually are in the hands of people of biology, okay, to solve problems in graphene. This is important, at least in the mechanical or chemical activity. Well, there are some experiments for IgG or BSA. Many of them are just at microscopic level, not at atomic level. And as I said before, IgG tends to absorb in planar configurations. And from the theoretical point of view, there are simulations on small, short proteins or short peptidic chains. And in this case, most of the simulations show that graphene is not compatible, biocompatible. This means that when you put some small molecule on top of graphene denaturates and folds, and it loses the tertiary and secondary structures. Okay, these are bad news. If you want to construct a biosensor of graphene, for instance, you need to be sure that the graphene is biocompatible. And of course, on the contrary, you will destroy it yourself. Okay. Well, then these are bad news for sensors, because on the other side, there is a family of biosensors in which you have cantilever with the IgG. Okay, you put the IgG molecule on top of cantilever, and these two domains here are used to connect with other proteins in the system, with antigens. Okay, this means that if the configuration is flat, the activity will be lost. then this means that graphene at the beginning it seems that this is not good candidate for constructing biosensor devices. Well,
excuse me, but if this protein always prefers to be flat on, no matter what is the surface you take, it will be flat on. So,
yeah.
so then maybe it's not the surface that is wrong, maybe it's the protein that is.
You are right. But the idea is that there are a lot of issues, questions to be analyzed in this IgG and BCA absorption of graphene. Okay, and we decided to study this because we have experimental results that say the contrary. Okay, then the idea is that from a long time ago, the Carlos Garcia group is just an expert in making this kind of ecography. Okay, at least simultaneous maps of topography and elastic properties of the molecule. This is the IgN, it's a different configuration of this immunoglobulin protein with a pentamide. And this is the topography, okay? This is the topography. The modulus, the Young modulus, local Young modulus of the protein. This means that we can perform experiments in order to detect. But of course, the mechanical properties doesn't depend on the topography. Okay, there are some correlation, but it depends on the strength of the internal configurations just on the other side of the border. Well, this was the reason to perform more experiments in graphene, but we discovered that graphene is not denaturized. It keeps the shape, okay? Then this means that it seems that graphene is good in the sense that we keep the shape of graphene, but we discovered that there are many different configurations, not the flat one only. Okay, then this is the reason we start with these preliminary experiments to say what's happening here, what is the way in which graphene absorbs on the surface, what is the structure of this molecule, and how we can start information with the EFM. Then we are from theory, not theory, from computation, and then we are very stupid sometimes. Then we try to put all, like the students, these young students, in the machine and to get the answer, and it's a lot of numbers, okay, to see what happens. Okay, we try to use the first approach in which we mimic the experiment with the tip formed by a carbon nanotube, the protein, water, and the surface, and make the same. To use the tip, to indent the tip, etc. But we have several problems. The first problem is that when we try to press the tip, the molecule slips away, and okay, it didn't keep the position. And in some cases, the molecule denaturize. The IgG molecule start to denaturize. Then we stop, okay, we were a little bit clever and decided to split the protein in several small problems to see what's happening. The first is just to study the role of water in all this business, the interaction of the protein with the surface, and the role of the tip. Okay? This process, we are just, at this moment, we believe that we have the solution, but this took something like 3 years. Of course, we are just handling systems with 0.5 million to 1 million atoms. This means that we are not observing in the quantum physics area. I came from the Sistemas group in the past. I did a lot of quantum mechanical simulations, but this is possible to perform with. Okay, with quantum mechanics, you can solve maybe 10,000 atoms. Okay, you can use continuum or coarse-grained models. It's okay, but in this model you lost a lot of interactions, information about interactions, in particular hydrogen bonds. Then we use one tool that has been recognized recently in the Nobel Prize of Chemistry, that okay, you can combine classical Newton law physics with some information coming from quantum calculations. Okay. And we have used very standard software used in biochemistry. Amber, there are several packages, but we use at the very beginning Amber, in which you represent all these kind of motions, the stretching, bending, and torsional motions with very simple parabolic, and in some cases cubic, like not so complex parameters that you extract from quantum simulation calculations. Okay, and also you can add van der Waals, electrostatic, and hydrogen bond terms. But you should think about the number of parameters you would need to enter in these kind of situations. Huge number of situations. Well, first, protein-water interaction. There are two methods. The first method we tried to use was the cheapest. Okay, the cheapest one is the implicit method, the implicit solvent method, in which we replace water molecules by a system, like a sponge, surrounding the molecule, a continuous material, okay, with the same dielectric properties of water. And this is just the standard method that is used in studying the block, the connection of proteins, the docking of proteins. Okay, this is not, it's really very, very well known and it's used all the time. And this is one of the reasons we use it. Why? Because you save 90% of atoms. Would you remove from the simulation, you are making simulations of the order of 100,000 atoms or 1 million. Okay, and this, you put in the computer these numbers, and you see that the convergence time depends on the number, it's like a square or cube. You save a lot of time. A lot of time means 1 day, 3 months, 4 months. Okay? But when we try to solve this using the standard approaches found in the literature, this is our results with the implicit water. You see that the protein starts to degenerate at some point. The protein denaturize, and if you continuously moving, then the protein will be destroyed at some point. But for us was a shock, because this is a very standard method. Just that all the company are using continually. Okay.
So you say that the method, so with this method, the simulation, the protein denaturalized, but in the real experiment does not. So it's something artifact of the method.
Yeah. And when you see the results with the explicit water,
down to the left, you have
okay, when you make the experiment computer, the in silico experiment with water in a split solvent, at least the molecule keeps its shape. Okay. Then there is a problem with the method.
And the honeycomb below this protein is graphene.
Yeah.
So it's bilayer graphene?
3 layers in this case.
Why is that?
But in this case, 2 layers, another 3 layers. But this is not important. That we can put even no graphene in some cases. But the point is that with no graphene, method works. 2 simulations, the explicit and implicit are the same. But when you put the graphene, the situation is not the same. This means that this docking maybe is valid for protein-protein coupling, but not for protein with graphene or large hydrophobic surfaces.
And you see changes when you go from multi to single layer graphene?
No, it's just graphene is not so important. The number of layers is not so important in this case. Well, these were bad news for us. Okay, we know from the experimental results the things, the material will be keep on time. That is, it doesn't denaturize. Okay, but the bad news is that we need then to use supercomputing machines in order to get the results. And we need to spend this long time.
You tried different kind of
Approaches. Yeah. We use two of them, 2, 3, but in 2 of them we get the same results, the denaturation, in front of. Okay. Then we know more or less the origin of this now, after a couple of years. Okay. But the point is that finally we decide to use this explicit method of what. This is a problem. For instance, you are just dealing with 100,000 atoms, 100 nanoseconds. With this kind of time step, 0.2 femtoseconds, the number of data you are storing typically is something like 2.4 exabytes. This means that you have to remove all the information in order to have some handy files. Okay, and then we reduce this amount to this, just neglecting, okay, 99.99% of the information we store. This is a problem, okay, that you get a lot of information, but you don't know how to treat this huge information, and how to store this information, of course, and how to read this information for the subsequent analysis. Well, once we know the protein-water interaction, how this works, we go to the protein-surface interaction, and we decide to use, okay, we know that there are several configurations that are, okay, stable on the surface of graphene. Then we invent these 4 configurations. The first one corresponds to the flat one, another 3 corresponding to the end-on, head-on, and sideways on vertical configurations. Okay. And for the BSA, just we are working with the second configuration. At this moment, we have only this configuration. Well, it's very important to define a protocol, an experimental protocol in silicon, in order to approach the system. Okay, you put the protein on front of that, and you expect and you wait for something like 2 microseconds. You see anything, because it's unlikely that the protein will move by itself using van der Waals interactions and just with collision with water. Then you have to force absorption somehow. This is the protocol we are using. Okay, then you apply small forces in some places, sulfur atoms. Okay, and you gently make the landing of the protein on the surface, and then you thermalize. Well, in the end, we typically have simulation of the order of 200 nanoseconds. This is a lot for these large systems. And this is this 0.1%, 0.1 per thousand of the we plot at the end. We define quantities like the gyration radius, this inertia moment is very similar, okay, or the root mean square deviation. All these quantities inform you are your panel in which you say if the molecule is converged, is denaturized, or in the form somehow. For instance, if you see this kind of motion here, in this configuration, you can correlate visually, okay, with the screen with the oxidation of the product. Well, then these are just all the information we can collect and we analyze. The final result is that all the configurations are stable. Ones are absorbed, we don't see any shift, tilt, whatever you want. They bond to the surface. Okay? They are stable. We can calculate the protein surface interaction, and we discover that these are strong numbers, okay, that the results are well converged. And we can calculate the surface of contact, just seeing the same. And in particular, we can correlate both the interaction energy and the surface energy and the contact surface area. We see this linear connection. Okay, the larger the protein contact, the larger the interaction. It's very distinct. But important is that this slope is very close to standard local density, beyond local density with van der Waals correlational calculations. Okay, the slope is 0.3 in this case, and this case is 0.28. This means that all the interaction is van der Waals in this case. The important interaction for the binding of protein came from the van der Waals interaction. Even we know which are the groups touching the surface, and we see that there is no difference. There are 0.5% from hydrophobic groups and 0.5% came from hydrophilic groups. This means that there are no preferences on the kind of groups just in touching with the surface. There is no reconstruction of the protein in order to favor some configuration. Okay, this is important because this means that the protein is harder, is strong in order to resist the interaction, and it prefers to keep the shape, okay, by itself, not moving group, hydrophilic groups or hydrophobic groups to the surface. Yeah, okay. We can make, you have this picture here, or here, and we can compare the number of beta lamina, alpha helix, or loops before and after the absorption process for each configuration. We can see here that the beta sheet in the IgG case is almost the same. There is few, okay, there is a few loss of beta sheet or alpha helix in this case, maybe 10%. Good news, this means that the protein doesn't denaturize, it keeps the shape and it will keep for sure the activity. And we want to be sure what's the energy we need to remove the protein. Then we apply a known method, the Jastrzinski method, in order to dissolve, okay, the protein. This method is explained here in short. We make 10 extractions of the protein, and we average somehow the different works needed to make this extraction. Okay, for instance, this is a typical extraction, gives energy versus the mass, center of mass of the molecule. Okay, this is the average of several trials. Then from this value here provides you the information about the absorption energy. Here, these numbers here correspond to interaction energy, but this doesn't include water effects. On the contrary, absorption energy is mandatory to have to count water. Okay. Then we have calculated the absorption energy. We can compare with the interaction energy, and you can see that in the AGG case, numbers are very similar, maybe 60 kilocalories per mole difference, but it's not the same in the BSA. But this is logical. Why? Because this is hydrophilic and this is hydrophobic. Then the water is the water plays very different roles in both cases. Okay? Then the energy, interaction energy, and absorption energy are very different. Well, this means that we know that we have stable profiles, okay, and with reasonable energies, in the sense that all these energies here are larger than the denaturation energies. This means that when the protein, okay, is attached to the surface, it will keep there forever. And if I try to apply some force to remove it, I will destroy it. Okay? I will destroy it before be attached. Well, I come back to the experiment. I can make some scan on two directions and to get these profiles. In other case, I get this profile, and so on and so on. This means that I can say we can make the same with theoretical profiles. This means that I have a way from the computation to get the profile that helps the experimental people to recognize the kind of protein they have. These are the proteins, and this is the statistics. we measure something like 300 proteins, and we can say that the vertical configurations are larger than the flat configurations. Very important results, because this means that graphene is biocompatible and IgG molecule will prefer vertical orientation rather than flat configurations. We can make a very simple model. If you treat your molecule like ice, for instance, you have two possibilities for these flat configurations and another for the other one, the vertical ones. And this is the model is just like the sticky ties, in the sense that once you put the face of your molecule on top, it will be there forever. Okay, then you have 6 possibilities, 4 correspond to vertical orientations. This provides just a ratio of 2, very simple approach. Okay.
Which is the flip?
This means that you have this possibility and the other one. Okay.
But you started with a statement that in principle protein not compatible with graphene surface. At the same time, now you claim that it absorbed by it. So there is some kind of logical jump. I mean.
No, first was at the very beginning referring to the literature, in the sense that the current experiment for small molecules, small biomolecules, not large ones, on simulations on graphene provide denaturation. But in the case of large molecules, we see that it doesn't happen. In the case of large molecules like DSA or IgG, the molecule will keep the state, both in the experiments and in the computer. And all these are good news for biosensing, in the sense that it's possible to fabricate a graphene device with high probability to have graphene on the vertical positions, able to capture antigen bodies on the floor, on the floor. Okay. Then once we more or less know how to handle protein adsorption, we go to the tip. And we need, it seems very strange, but we need to create a protocol to approach the tip to the surface of the protein with very carefully, okay, in order to detect forces, to mimic experiments. And then we start with very simple problem, not protein.
Which material is the tip?
In this case, it's just the same. It's diamond, and we can use diamond or carbon nanotubes. But these are results in the literature, and they make this experiment, theoretical experiment, okay, approaching a tip to the sample. In this case, it's calcium fluoride, in order to detect this peak here that corresponds to the force required to break the water layer that it spontaneously is formed. Okay, you see you have water, but the last layer of water is pseudo-order. And then you need some force to break this layer of water. This is an experimental result, and these people here developed some algorithm in order to recover this experiment. Well, now in collaboration with Ciencia and Ciencia, they are just making friction experiments, okay, in water, in air, in vacuum, in graphene. And they are able to have atomic resolution with water. Then this moves us to collaborate with them because we have the technology. We expect to use this for molecules. The first approach is just to use this for graphene and water. First, we are able to use this code in order to approach the tip, and these are the results. Approach the tip, we are able to see here this peak that corresponds to the force needed to break this layer. Okay, this means that we have a standard tool in order to recognize this small feature, this structures here. And now we are just moving in parallel to the surface, the tip, in order to recover lateral forces And these are the results. We have demonstrated that we get in vacuum and water atomic resolution, just the same as in experiments. Then it's very simple. You don't need to make friction experiments on vacuum. You can reproduce experiments with water. Okay? And then we are just, this is a paper we have submitted to physical regulators a couple of weeks ago. And this is the experiment, okay, and these are the results for the experiments. Then this is just the last picture corresponding to protein surface, in the sense that now we are, after 3 years, in conditions to reproduce in the computer the experiment. Then we are just at this moment making the first trials on a tip, on the protein, in order to see what is the effect of the tip. Okay, the radius tip is very important. What's the effect of the position of the tip in the protein? It depends if you are just in front the tip, but you are in beta helix or alpha helix or beta lamina. Then, depending on the internal structure, you will measure different things. And this is very important for the project. If we want to make ecography of a cell or ecography of a protein, we need to know how to correlate things inside with the results. Okay. And finally, I will show you the results has nothing to do, more or less. This is not related with proteins, but DNA. And this is a collaboration with MECWIX, and a Spanish company. It's a spin-off company of the microelectronics of Madrid. Okay, and this company has developed different biosensors based on DNA double and single strand DNA cantilevers. And they base all the results in this paper here. More or less, things goes in this direction. We have double strand, okay, in this double strand DNA, and you increase the humidity in the system, the cantilever bends somehow. This means that you are putting more water molecules. The water molecules don't fit too much. They try to expand the system, and this is reflected in the expansion in the substrate and then the infection in the cantilever. But when you remove the water, you come back using the same path. There is no hysteresis in this case. But when you use single-strand DNA, results are totally different. Okay? At the very beginning, when you put water, the molecules, the cantilever deflection is just in the contrary direction. At some point, the situation will reverse, and finally you get in a very similar position. But then you get back using the same path. They explain a little bit more or less how it should work, but we prefer to make calculations on that. Then we have prepared in the computer the DNA array cantilever. We put all the DNA strands, okay, single strands. We can simulate this system. We can use here some periodic boundary conditions, and these are different. You will see. We use the same DNA chains that in the same density, a smaller system, of course, okay, and we increase water amount of the water molecules in the system. When we put 100 water molecules per single strand, you see this. There is amorphous configuration of holes, voids, okay, in the system, and the height of the monolayer is decreasing. But when you put more and more water, okay, you see that some changes. In principle, it seems that water helps tends to favor vertical orientation. Okay? But these calculations were done for fixed substrate. Then we can measure anything. Okay, we put some real cantilever. Now we have a flexible substrate, graphene monolayer, and we make the same experiment. We put water, and this is the result. At the very beginning, where it's in the non-dilatation configuration, you get this initial bending. This means that DNA chains interact each other, and they provoke this compressive stress. of the system. But when you add water, the compressive stress even very small. Why? Because water tends hydrogen bonds, okay, and force, and the water force the joining of these chains. But at some point, this bond saturates, and the water and the DNA molecule prefer to be stretched in order to enhance the surface to collect more water. Okay. Then the results are more evident. When we compare the height we get from the experiments in the computer and experiments in real life, the results are very similar. Why is? Because we are just trying to make some contact with them in order to optimize using computers the design of the biosensor. For that it's very difficult to reproduce many different kind of configurations, but we have the opportunity to solve this in the computer. And these are not so dramatic calculations, okay? They can be solved in half a day, more or less. Then we can prepare more configurations in our computers than they can solve this problem. Well, then a summary of my talk, we have discovered more or less that these implicit methods, well-known and used methods, are okay. We have to be treated with some special care. In the case of graphene, at least, that the explicit approach explains rather well, more or less, the configuration we see in experiments, that due to the interaction with people in computation, they have methods to recognize the molecules and make statistics, and that we have been developing this protocol able to detect adaptation layers, this level strength here. And finally, we are just improving DNA sensors for company, okay, using some supercomputing facilities. Well, and it's all.
So now it's time for
At some point you were mentioning that you have this harmonic approximation for the notional degrees of freedoms, but you could also take cubic and higher terms, which is the effect that you see any importance in considering these higher terms?
In general, these are things that physics likes to include, not biologists. Because biologists, they don't worry about nonlinear effects or non-harmonic effects. They want to know if the molecule is stable or not. If the molecule is acting in some direction against another molecule or not. Then there are some force fields that include this. Okay, but this is you want to make some kind of fine analysis you want to compare with some Raman, for instance. When you make Raman experiments and then you have but this doesn't correspond to the biology field. In general, these things are just only thinking in the range of physics. You look at it in physics, not in biology. Then there are little results about that. There are fields, okay, force fields developed with this, but this very, okay, figure out that you spend 1 month of calculation. Then, when you are just asking for 1 month, you need some results of interest in biology community, or health community, and are not so useful for them.
Some more questions?
Yeah, I have question. I mean, you say that basically you get absorption due to size of molecule. Then, of course, one question arises. Can you define the critical size when it started to absorb? This is one question. And second, it's more deeper. What is the mechanism which creates this type of cooperative phenomenon? Because if you have small molecule doesn't absorb, suddenly you have some critical size that start to work.
Good question. In fact, we are just working with some models of molecules. We know that BSA is something like we know that molecule with 50 amino acids will denaturize. Then we are selecting some molecules in the mean, okay, 100, 200, 300. But it's not so easy to select these molecules, so, because we want to molecule globular shapes, like in BSA, and we are just running at this moment. We discovered that it's stable, for instance. This means that molecules that denaturize should be of the order of 100 amino acids. But in real life, 100 amino acids in this database are few molecules, in this few proteins with so many.
Do you have any clue what is the reason why the dielectric approximation is not working for the interaction of both of those?
What we know that when we make the simulations and we have all the components of energy, and we know that the van der Waals component of energy between graphene and surface protein surface are very the distance is very short, is overestimated. And this is one of the reasons why the protein then tend to expand on the protein in the implicit method tend to expand on the surface and be destroyed. But I'm sure that they didn't think to use in the past business absorption. This method is designed for the molecule alone or the molecule in front of another molecule.
Maybe it's a stupid question, but I understand this electrostatic approximation is that you change the dielectric, you take the material as a continuum with a different constant, so it's not vacuum, it's whatever which is suitable for treating water. And that fails, but this is because you assume that this medium is the same everywhere.
No.
So what if you take a medium that has a dielectric constant that changes from, so at the surface is the one of the vacuum, while outside the surface is the one of the water, and say with a linear gradient. Would that?
No. In fact, the approximation fails exactly when you have the hydrophobic approximation. You have an hydrophobic surface, IgG is hydrophobic, and you see the failure when there is a first layer of water between both, and when this first layer of water is formed, the approximation starts to fail. Because in the continuous model, this one layer of water cannot be treated. Okay.
But if you take, I mean, put that, I mean, something like a dielectric constant that changes according to the distance to the surface.
There should be a way. But there are also another thing that is very important to know, that when we add water in a realistic manner, that you are using stochastic collisions that help you to stabilize, for instance, in this case, the vertical configurations. It's very difficult. The system evolved to a vertical configuration from DNA when you use the
collisions are mainly on the direction that forces the molecule to stay.
It's very important to have this in DNA. This is a small chain. I mean, this small chain, the presence of water is fundamental. They encourage you to put in vertical, in the stretch position, the molecule.
So I have just maybe the last one. So try with the graphene, but can you try with other 2D materials like CSIC or these new materials?
Okay, using different software. No, different software. Because in this case, Ampere is well prepared to carbon. But if you want to study, for instance, different material, then force fields are not so good. Then you have to move to another. This is one of the reasons we treat the original experiment were on mica. But this problem cannot solve mica. Okay. From the theory to graphene, and then Ricardo Garcia made the experiments in graphene in order to compare with the simulation. The story is a little bit different. But the idea is that we couldn't solve mica or silicon oxide, for instance.
theoretically, could you expect the same behavior?
Yeah, of course. The idea is that some people is making these experiments, but in graphene oxide,
Yeah.
for instance. But we, at this moment, we cannot solve well graphene oxide because oxygen, well, the stoichiometry of graphene oxide is not known, okay, at this moment. Then you have to make something like to put oxygen atoms at random, something like that. But there are experiments on graphene oxide for a substrate for biosensing.
And there is any rule in which you throw away the 99% of your data? Or it's kind of random?
It's,
So you
it's
can
just,
pick up?
okay, we have this external disk of 2 terabytes that we need to study 4 proteins, 0.5 terabytes per simulation, in order to have one drive, an external hard drive with 4 data, with 4 simulations. It's just the rule at this moment. Okay, this is a problem because we know that we have information to make comparison, for instance, with vibrational modes. But then we need to store a lot of information to make Fourier transform, outside correlation of velocities. Okay. Then, but there are some experimental data that's making this, people making this at this moment. They want to see if they are able to recognize some denaturation using vibrational modes in quality centers, for instance.
So, last question?
Just something about the now, like, am I understanding correctly? This is a graphene layer which is bent by the hydration of the...
Yeah, the red molecules, at the very beginning we put all the molecules just on top, and we left free just in order to get down.
And you observe this chemomechanical effect, right? And this has been also observed in experiments?
Yeah, this is the experimentally is just the cube that I showed in the list. It's just the last. We observed this through the cantilever bending, this here. Then at the very beginning you have a contraction due to the presence of water, that the water helps to glue, to attach each other the DNA. But at the end, water tends to put the molecules in this stretch configuration vertical to the plate. Okay? Then the biosensor is based, this biosensor is able to recognize a change in the DNA sequence. Okay? You read the paper, is very clear. But it's very costly and it's very tricky the way in which they create the DNA array. This is one of the reasons this is not transferable to health system, for instance. It's very expensive. But they want to know if they want to make some version with a small number of arrays, a small number of DNA in the array, or use the same way the way of thinking in order to develop new sensors. Okay, but the first is very interesting, but it's very expensive to transfer to the system. The system is very unrealistic, and it's very costly just for detecting only one change in the DNA. This in some cases makes no sense. Maybe this can be used as in a control for controlling processes, for instance, this kind of sensor, but no as a standard way to characterize DNA in hospital.
Okay, so I think that we can stop here. We can again thanks our speakers. So we will do that this evening. We have another talk on
aparte de los números que hacen viables con efectos secundarios, ¿hay alguna curiosidad a cuánto lo que os esperáis puede salir de ahí?
Es complicado. Lo que sí es cierto es que sabemos que hay una parte que tiene que ver con lo que no está aportado. Nosotros, hay varias cosas. Primero, todos estos sensores, teóricamente, la ventaja de tener es porque al final hay un traductor electrónico que es el grafeno. El grafeno va a tener...
Para él.
Porque no sabemos realmente... Todo es
Con mi nombre,
una especie que es un árbol de Navidad, con dos ramas SAB arriba. Va a cambiar tanto la configuración electrónica del sistema para que el transporte abajo sea distinto. Eso todos estamos vendiendo aquí una moto de que esto puede ser un biosensor. Vale, pero luego en la realidad, es decir, en la vida real vas a tener un grafeno, vas a echar tus biosensores, tus inmunoglobulinas, sabes que el 50% van a quedar en una configuración no útil, un 40% se pueden salvar, pero ese 40%...
Sería una barra de error enorme, ¿no? De esto que eran resolved.
Entonces, el 40% cuando yo, primero, ¿cómo fabrico de forma estandarizada esto? Todos van a ser iguales, son distintos, parece que van a ser muy distintos. Pero cuando nosotros estamos calculando, que nos lo he mostrado,